Hello everyone, in the series of basics of software defined radios and practical applications, we were discussing the power amplifier, their classes and parameters. Today we will cover the power amplifier lineup for linearity and power requirement calculations. So as we have discussed earlier also, the main criteria for PA selection is dependent on its gain value, how much output power it can give, efficiency, and while we are maintaining these three values, if we can maintain the linearity of the signal also. So, the selection of devices for any particular requirement, this is what we will target today. Now, PA assembly can be of two types. If we have a series of n PAs, we can attach them in series or we can assemble them in parallel. When the PAs are in series, basically if you look at its three characteristics, means gain, output power, efficiency and linearity, how it will behave. Suppose we have n amplifiers and each of them has a gain of G. So, G1 is representing the gain of first amplifier, G2 is representing of the second, and Gn is the gain of the last stage. So, total gain in this case, if it is in dB, it can be given by G1 dB plus G2 dB plus Gn dB. If it is in its ratio form, the ratio of two voltages, then this G will be simply G1, G2, G3 and Gn. So, gain is simply the summation of all the terms in the, if they are given in the logarithmic form, or multiplication if they are given in the form of ratios. Now, coming to the second point is the output power. Now, output power of each stage is defined by P1 dB point of that particular amplifier. So, that P1 dB is the maximum power which this amplifier can provide, and if we want to have more power than this P1 dB power, then it is possible that our device will burn if we will give it more input power. So, we have to be careful about P1 dB of each of the stages. So, at any stage the output power should not be beyond this P1 dB power. Now, the output power is covered here, and we know that the efficiencies, all type of efficiencies, DC efficiency, simple total efficiency or power added efficiency, basically they are the ratios of the powers. So, output power divided by input power, which I mean to say DC power. So, basically we have input power which is RF power, we have output power which is again RF power, amplified power, and then we have PDC, the power which is provided by a DC supply. So, this DC supply is giving power to this amplifier, so that this input power has that gain, so that it can go to P out. So, efficiencies are always decided by these P's. So, as long as we are able to do the calculation of power, output power, we will be able to calculate our efficiencies. Now, the fourth requirement is linearity. Now, linearity is mostly seen in terms of carrier to intermodulation distortion of third order. By third order, we have covered it earlier by two-tone test, that the third order products, they are the one which fall near to the original signal. So, if it is two-tone test at F1, F2, and this is the frequency, and it was the signal amplitude here, in that case the third order modulations, which is 3f1 minus f2 and 3f2 minus f1, they are the nearest one, and others fall much farther away, which are harmonics or the higher order intermodulation. So, whenever we are talking about our intermodulation, mostly we are targeting our third intermodulation, and C by IMD is the one for which we target. So, we have covered the parameters earlier. Now, we will see that how we can select our device to actually achieve a particular parameter for according to our requirement. So, let us again take our example commercial data sheet, for which we had done the exercise of reading all the specification of the power amplifier. Let us say this is the only device available to us, and by using this particular power amplifier we want to achieve a particular set of requirements. So, let us have the problem statement in front of us. We have to use the PA with the given specifications in the data sheet, and we have to propose a lineup to design at least a 10 watt average power and 80 dB gain power amplifier for a 3G base station which is driven by a LTE, 3G or 4G signal. Main requirement here is that this signal has a peak to average power ratio of 10 dB. This amplifier has to meet a linearity of C by AMD3 of 45 dBc, and it has to avoid clipping the signal. Now, we have to specify the output power back off operating point for each of the power amplify stage, the gain of each stage, as well as linearity of the finally designed amplifier. So, let us first of all review what are the given specification. Let us have a look at this commercial data sheet and let us note down those specifications because we will be using those. So, what is given is a typical gain for this device is given. So, typical gain is given as 40 dB. Do we know the saturation power? If we look here, the output power at 1 dB compression, it is the P1 dB point. So, it is given as plus 37 dBm. So, output power P out for P1 dB is plus 37 dBm. Now, what else do we require? Gain and P1 dB is known, and okay, when we are talking about linearity condition, then IP3 is also given as plus 49. So, this is the given requirement here, and we have to design a system so that we are able to qualify all these criteria. So, while we are starting these calculations, first let us review our conditions of linearity so that we can apply this formula wherever applicable. If we see here the relation between IP3 and P1 dB for the SSPA, it is given by this formulation, means the P1 dB is equal to actually IP3 minus 10. So, if we are knowing the IP3, we can calculate our P1 dB from here, but in this case we know both of them, we know our IP3 and we know our P1 dB. So, if we see here, it is holding that relation almost. 49 minus 10 will be 39, which is near to the plus 37 dBm. So, in a case when you are not given this value, you can calculate the approximate P1 dB point for the SSPA from the given value. So, in this case we will do our calculation from here, and again it is the approximate calculation, but it gives you idea to select your power amplifier. Now, if your P in 1 dB is given, then you can convert P out 1 dB by using this formula, small signal gain minus 1 plus P in input power 1 dB point. If you are given P out at that IP, when you are also given IP3 power, then you can use the formula C by upon this which is carried to IMD3 ratio as this formula. Now, because we are not talking about any particular P out, but the maximum P out. So, first of all we will do the calculation of maximum P out, and then we can either use this formula or we can also use thumb rule for the SSPA I upon C upon IMD, which is 20 plus 2 times output power back off. So, these are the formulas we will be basically dealing with. And what are the steps for this? First of all, we have to calculate the output power back off for required C by MD3 for solid state power amplifier. Now, looking at our problem statement, we require at least 10 watt power from our power amplifier. So let us convert it back into dB, logarithmic scale, because most of the calculation will be in terms of dB. And if we see C by MD is provided in terms of dBc, and our gain of the power amplifier is given in terms of dB. So let us calculate this output power into dB first of all. So required output power from PA system. I am calling it system because eventually we will select number of power amplifiers to make this system. So the P in watt is given as 10 watt. So P in dB will be 10 log 10, which is actually 10 dB, and P in dBm will be P in dB plus 30. This was the relation. So 40 dBm. So we should be able to get 40 dBm average power. Now it is also given that we should avoid clipping of the input signal, and this signal has the peak to average power ratio of 10 dB. So if we do not want our signal to clip, then actual system should be able to stand or able to provide P dBm, which is calculated here, plus PA PR. So whenever the signal peak will be here, it should not be clipped. So power amplifier will be working at this average power, but the signal peak will be sometimes reaching to this P dBm plus PAPR value. So it will be 40 plus 10, which is 50 dBm. So we know that we have to have 50 dBm actual system power from here. Now let us do our calculation for this system. Now we have to find output power back off for required C by MD 3 for SSPA. So for SSPA we had seen that we can apply this formula. If we know the C by MD 3, we can actually calculate our output power back off. So let us do the calculation. C by IMD 3, 20 plus 2 times output power back off. So it is 45, or output power back off would be 25 divided by 2, all 12.5 dB. So our signal will be actually driving at 12.5 dB power back off from whatever our signal can actually provide to us. Now what was the power amplifier? P1 dB output power plus 37 dBm. So basically power amplifier can provide this much power output power at its 1 dB saturation, but because we have to maintain the linearity requirement of 45 dBc, that's why we should work at 12.5 dB back off. So P out possible for PA to provide at 1 dB compression is 37 dBm, but because we want to maintain this linearity criteria, we cannot work on this output power. We will work at a output power which is much lesser. And how much lesser? If we remember, P in versus P out, we have discussed this, that if it is the output power, then this is what we called output power back off, so that it can work in the linear region. So, as higher OPBO, higher is the linearity, and as lower is the OPBO, it is near to the saturation point, and the this C by MD3 will be reducing in size. So, for this calculation, PA will be able to provide 37 minus OPBO minus 12.5 . So, to maintain this linearity requirement, the power amplifier, individual power amplifier will be able to provide 24.5 dBm power only. Now, how much power we require? This much. And how much this is providing? Single PA is providing this much. Now, keeping this in mind, let us move forward with this calculation. Now, this particular PA which we are studying, and specifications are given here, we are able to get only 24.5 dBm from its output, because we have to maintain the C by MD3 ratio of 45 dBc. But we have to achieve 50 dBm from this system. So, how can we do that? If we add two of such devices together, their output will be the summation of these two. So, the output power will increase. So, from here we have this idea, if we keep adding these power amplifiers in parallel, then their summation might eventually reach this value. So, now let us do the calculation that how many of these devices we have to put in parallel to achieve that output power. So, how can we do that? Suppose we have V voltage from a system and V voltage from other system, and we are summing them together, and we are doing the calculation in dB, then what will be the increase in the dB power or dB conversion of this value particular. So, suppose if it is power, like the power here, then I am talking about the logarithmic calculation at this point and at this point. So, at this point P dB is equal to 10 log 10 P. If I increase this power and I calculate P dash dB here by adding these two similar branches, then P dash dB is actually 10 log 10 and this is watt power. So, let us say 2P. The power has doubled in the watt value. So, in the dB scale it will be and this value comes out to be so, from here we see if we add two branches and each of them has a power of P in the logarithmic scale, then by adding those two identical branches our new power will be just the addition of 3 to the old power factor. So, keeping this in mind, we will do the calculation of our number of devices here. For example, for 24.5 dBm at the output of this P and PA, their summation will be 27.5 dBm here, right. So, what is happening here? If we put two devices, let us say P's in parallel, we have increase of 3 dB. So, the eventual power will be 3 dB plus original P dB. If I put again these two devices in parallel with other two devices, then it will increase by another 3 dB, right? Or I say that I repeat this block here and add them together, then it will be what? 30.5. Another 3 dB increase will be there, and there will be 4 devices in parallel. So, 4 devices or PAs will give rise to 6 dB plus PdB. If I increase it to 8 devices or PAs and again repeat these here, then the addition will be 33.5. So, it will be 9 dB improvement over the original PdB, right. So, if you look at this trend, the number of parallel devices are actually 2 to the power n, and this n is actually P out minus original PdB, this is also in dB, divided by 3, right. So, basically 9 dB plus PdB minus PdB will give you 9, and divided by 3 will give you 3, and 2 to the power 3 will be actually 8, right. So, this will be number of parallel devices 2 to the power n, where n can be calculated as output power minus input power both in dB divided by 3. So, let us use this calculation here to know how many devices do we require in parallel here. So, n, which is number of devices, will be P out, which we require as 50 dBm minus input PdB, and that input PdB which was for only single device was 24.5 dBm divided by 3. So, let us do the calculation from here. So, n equal to 8.5. Of course, n is number of devices, number of PAs, it cannot be 8.5. So, let us go to 9, select higher number of devices. So, we have chosen n equal to 9. So, number of devices will be actually to the power n. So, 2 to the power 9. So, it is quite a high number here, right. So, we have to add 2 to the power 9 amplifiers, so that we can have 50 dBm at the output, so that we can have C by IMD3 ratio of 45 dBc. So, 2 to the power 9 amplifiers here. Now, of course, there are so many amplifiers that it is not a good idea to use actually this device for this specification. What is even better? If we choose a device with high P1 dB, suppose if it will be 46 dBm, with that 46 dBm we will have very high value of this calculation, and if this value is high, then we will have less number of devices here. For example, our P out we require it to be 50, and suppose our PdB at this stage can be 44 here, then it will be 50 minus 44, 6 divided by 3, only 2 to the power 2, 4 devices we have to connect in parallel. So, if you have to do connection in parallel, try to find high P1 dB value devices, so that you have to use lower number of devices. So, anyhow we are able to calculate here our last stage, and this last stage is able to give us 50 dBm of the output signal, so that our signal is not clipped. It is able to give us 40 dBm average power or 10 watt average power as was required. Moreover, what was our other requirement here? Other requirement is that we have to have 80 dB gain from this power amplifier. So till now what is missing? The gain here of each amplifier is only 40 dB, and because they are in parallel, they all will be giving only 40 dB. So the gain of this whole system is only 40 dB because they are in parallel, right? So difference from here to here is always 40 dB. So we are not getting our 80 dB gain requirement, which is a must for this design. So now what we can do? We have designed our final stage, which is this stage. Now we have to have one stage before this. So output, and we have chosen our devices here. N equal to, which is number of devices here, 2 to the power 9, and this will be input, right. So at the output of each device we had 24.5 dBm, and eventually we had 50 dBm at the output. Now the system gain is 40 dB. So what will be input power? 50 minus 40, so 10 dBm. Now this 10 dBm is the requirement which any power amplifier which we are going to attach here should be able to provide, and because we are using the same power amplifier, we know that what was its requirement there. It was able to provide us 24.5 dBm at the output, right. So 10 dBm it can easily provide, it is within the range. So now what we have to do, actually we have to just simply attach one of the device is with which has already 40 dB gain, and it is able to cover this requirement of P out of 10 dBm, because it can give up to 24.5 dBm, so it does not have any problem. Now let us check that what will be the output requirement at the output power backoff to maintain the linearity. So if at the output level our C by AMD3 was 45 dBc, its previous stage should have even better C by AMD3, otherwise the intermodulation term which are coming from here, it will be input to this one and they will become even more nonlinear. So the C by AMD requirement becomes higher for the first previous term. So for PS term, let us take even better C by AMD3 requirement, let us say 55 dBc. Okay, it has to be always better than this one, and as a rule of thumb we try to take almost 10 dB better than the last stage. So for this C by AMD3, what should be the power output backoff? C by AMD3 equal to 20 plus 2 OPBO, again because it is again the small signal power solid state power amplifier SSPA. So we can use this formula. So 55, what should be the output power backoff? So 17.5 output power backoff should be there. So actually output power which we require here is even lesser. So output power required at stage 1, and let us call it a stage 1, is 10 dBm minus 17.5 dB. So minus 7.5 dB. Now again we require minus 7.5 dB and our PA is able to give 24.5 dBm. So we are very safe from that point of view. Now our system is from here to here. So we have to give the specification of each stage, how much output power back of operating point we have to keep, the gain of the stage and the linearity of the finally designed amplifier. So G is 40 for both of them, OPBO was 17.5 dB here. The previous stage here it was 50 minus 12.5, so it was I think 15.5 dB. We are maintaining C by MD3 of 45 dBc because we have done our calculation for keeping this linearity requirement, and we are getting our output requirement of 50 dBm. So our signal is not being clipped and we are able to design the system completely. So this was one example, and we can, if our requirements are not achieved, we can keep repeating this for the previous stage. What we can see from here, we could have reduced parallel devices if we choose high P1 dB PAs, then we can reduce this one and we can reduce series PAs, number of series PAs if we use high gain PAs. So for example, if these PAs were able to give us 80 dB in one shot, we are not required to use this stage. We should be able to get everything from this stage only. So keeping this in mind, in the next lecture we will do the mix and match up of some of the devices to choose the best among these. So this was the lecture where we covered the requirement and how to choose the specification. Thank you.